And Galilean relativity was a very successful and useful theory, and indeed almost necessary for science, because if the results of experiments kept changing as our velocity changed as we move around the sun, then things would have been too confusing to figure out. And indeed, Galilean relativity was the foundations of Newton's work on mechanics and survived unchanged for a couple of centuries until Maxwell came along and completed his theory of electromagnetism. Maxwell's equations are: now in a vacuum we can decouple these equations by taking the curl of the last two, where we just use a vector identity on the left and took the derivative out on the right on each side. And then because we're in a vacuum, this div is 0, and from Maxwell's equations that div is 0, so we're left with, which Maxwell noted, have a wave solution, with a wave travelling at speed c. Now this c here was actually based on electromagnetic constants, and this mu naught and epsilon naught were determined by electromagnetism experiments rather than experiments on light. And of course, the fact that the wave solution did have a speed at the speed of light was incredibly suggestive. And famously, James Maxwell proposed to his wife Catherine by taking her out, showing her the starlight, and telling her that he was the only one on the planet who knew what that light really was. And Catherine obviously forgave him his pride because she did say yes. But nevertheless, one of the great mysteries had been solved. The nature of light had been debated for many years, and indeed 50 years before, Young had finally shown the light was some kind of wave, but people didn't know what kind of wave it was. And then Maxwell, through this process, showed, yes, it must be fluctuating electric and magnetic fields causing each other that propagate as a wave. But of course, there's a key question that we've just prepped ourselves for, because if we discuss Galilean relativity first, which is, if it moves at speed c, what does it move at speed c with respect to? So all other waves move through some kind of material. The wave in a guitar string is moving through the string, a water wave moves through water, sound tends to move through air or whatever medium you're in. So what does an electromagnetic wave move in? Well, they invented something for it to move in, a kind of luminiferous ether that spreads throughout the entire universe. But if you're going to invent something like that, you have to do some kind of experiment to show that it really exists. And the experiment they did was to try and look for changes in the velocity of light compared to how we were moving with respect to the ether. So it'd be very, very lucky if the ether happened to be completely stationary with respect to your experiment. And indeed, if you've got the sun and you live on a small blue ball circling around the sun, then at different times of the year you're traveling in different directions. And so if the luminiferous ether is sort of spread out through our galaxy in a particular direction and moving in a particular direction, then at different times of the year we must be going in different directions with respect to it, at quite a different velocity. So the velocities involved here should be enough to detect the difference in the speed of light. Now, especially 100 years ago, it's quite hard to tell absolute little changes in the speed of light, but telling relative changes in the speed of light is comparatively easy. So the Michelson-Morley experiment took a light source and a beam splitter. They had the light bounce off the beam splitter, go up to a mirror and come back. And they also had some light go straight through the beam splitter, bounce off a mirror, come back. Then they would detect it here, and of course they would get constructive or destructive interference here, depending on whether these two light waves were coming in or out of phase. And the phase of the two light waves would depend both on the path length difference between these two arms, and also on the speed of the light as it travelled. And as you may recall, the speed changes whether you're going upstream and downstream or whether you're going across the stream and back. So they tried this experiment with many different orientations. They tried it at many different times of day. They tried it at many different times of year, trying to see if there was a speed of light changed between these two directions. And the result was they saw nothing. So there were a large number of explanations put forward for this. One of them, which was fairly quickly discounted, was that there wasn't any ether. The reason that was quickly discounted was the electromagnetic wave has to wave in something, right? Other explanations were that the ether was in fact there, but it was being dragged around with us. It had some viscosity, and as the Earth was moving around the sun, the ether was being dragged with us. So in fact, the experiments were more or less exactly at the same speed with respect to the ether all the time. Of course, if you have a completely stationary ether being dragged around the Earth, then what that means is that distant starlight is going to have to go through this kind of boundary, and it's going to be different at different times of year, so you'd expect aberrations from the starlight to be seasonal. No such aberrations were seen, so this idea of frame dragging was eventually disproved. Other much crazier ideas included, supposing you're moving in the direction of the ether, then everything gets shorter. So if this was moving upstream and downstream, then if that length actually got shorter, then you still wouldn't get any interference. So maybe that would explain why there was no interference. Such ideas were thought of as fairly crazy, although people did work out exactly how much it would have to get shorter in order for it to all work. So that was the stage upon which Einstein made his really big jump. So his big jump was to take two simple postulates and then take them to their logical conclusion. The first postulate was extremely non-controversial. It was simply that physics was independent of which reference frame you're in. Now there's a couple of things to mention about this. The first is this word inertial. An inertial reference frame is a reference frame moving at a constant velocity with respect to another one. The second thing to notice about this postulate is that it's exactly Galilean relativity. It's saying nothing more than if you're moving at a constant velocity with respect to somebody else, then you can't tell the difference between your experiments and their experiments. Now Einstein made one other assumption for his theory, and it was a much weirder assumption. He said essentially that there's no such thing as ether, and that light propagates in a vacuum isotropically, it means in all directions, at speed c in all inertial reference frames. If it happens in one inertial reference frame, then it must happen in all inertial reference frames. In other words, he's saying that the Maxwell's equations as written down aren't with respect to some kind of ether, they're with respect to any coordinates. And because one set of coordinates is just as good as any other set of coordinates, it must be true for all sets of coordinates. Now, if that's true, then we'd have to change our understanding of how space and time coordinates between different inertial frames are related. Right? All of that is up for grabs now. And so let's take these postulates and look at their implications. Okay, let's assume that we have two sets of axes. So we'll have a reference frame. Our reference frame is just a set of axes. So we're going to have our origin. We'll have an x, a y, and a z. We'll call this reference frame S. It's also going to have a clock, obviously. And we'll have another reference frame, which we will call S dash, which will have a y dash coordinate, a z dash coordinate, and an x dash coordinate. And there'll also be a t dash direction as well in time. Now these two inertial reference frames, we're going to assume they're both inertial reference frames, so they have to be moving with respect to each other at a constant velocity. And the standard way of setting up is we'll have S dash moving with respect to S at a constant velocity in the x direction. So have a constant velocity v. So in other words, the origin of S dash is traveling away from the origin of S along the x direction at a velocity v. And at time t equals 0 and t dash equals 0, the two origins are on top of each other. Now we can immediately say things about the transverse relationships between y, y dash, z, and z dash. We can do that from this thought experiment. Suppose we have a basketball and a hoop. Now suppose the basketball just fits through the hoop and it's traveling down at a velocity v. If that basketball just fits through the hoop, then we know what's going to happen. It's going to go through beautifully. Of course, by declaring that the hoop is stationary and the basketball is moving, we've got an implied reference frame, the reference frame defined by the hoop. And if the transverse dimensions, the y dash and the z dash, were to change, then we might have something strange happening with the ball passing through the hoop or not. So if the basketball were to get larger, if the transverse dimensions were to get larger as velocity became non-zero, then the ball would stop fitting through the hoop. So we know they can't get larger, they can only get smaller. However, this choice of reference frame is not unique. We have to get the same results of the experiment. We have to have the ball going through the hoop in all inertial reference frames. And the other obvious one we can choose is the basketball's reference frame. And in that reference frame, the basketball is static, and it's the hoop that's moving at velocity v, only this time up. And so if the hoop, we know it's not allowed to get any bigger, if the hoop was to get smaller, then the basketball would stop fitting through the hoop. So we know that the basketball and the hoop cannot be getting smaller or larger in any reference frame. So we know that y dash and z dash have to be equal to y and z respectively. Now this is extremely intuitive. Everyone's very comfortable with the idea that if you throw things, they don't change size. And so, although those relationships, we've just proved them from our axioms, they weren't too strange. What's a lot more strange is what happens to x dash and t dash.